Hello everyone, welcome to my channel. Today I am excited to walk you through my oil pump monitoring system project. So basically, this is a full stack IoT simulation that demonstrates how we can monitor industrial equipment like oil pumps in real time. So basically, in industries like oil and gas, equipment monitoring is crucial. So a single pump failure can cost thousands of dollars per hour in downtime, not to mention safety risk. That is why I built this system to show how modern web technologies can solve these real world problems. So in this video, I will cover first one, the overall system architecture and how data flows through it. Second one is the technology decisions I made and why. And the third one is how I developed everything to the cloud. And the fourth one is a live demonstration showing the system in the action. So let's first of all get started with the architecture. So first of all, I will give you the system architecture overview. So the system I have built consists of basically five main components that work together to collect, process, stores, and visualize data from oil pumps. So first we have the data producer. So in a real world scenarios, this would be IoT sensor attached to the physical oil pumps. But for this project, I have created a simulation that generates realistic sensor readings, including pressures, temperature, vibrations, and fluid dynamic matrices. These readings are basically sent to the Kafka clusters, which serves as our message broker. Now, I choose Kafka because it is highly scalable and provide exactly once message delivery guarantees, which is crucial for industrial monitoring where data loss is unacceptable. Then the second next is the data consumer, which picks up messages from the Kafka, validates them, process them, and store them in our database. This service also exposes a RESTful API that the front end uses to retrieve the data. Then for the data storage, I am using PostgreSQL, which is a robust relational database. I have designed the schema with the separate tables for different categories of the measurement, which allows for efficient querying and storage. Finally, the Angular frontend provides a dashboard that visualizes the data using charts and graphs. This gives maintenance engineering a clear view of pump performance and helps them identify potential issues before failures occur. So, you can see the images of the front end. It is currently not deployed, but I am trying to deploy it in the Google Cloud platform, which is under the development. Now the data flow looks like this, like our simulated sensor generate readings which are published to the Kafka. Then the consumer service process these messages, store them in PostgreSQL and makes them available through an API. Then the front end then fetches these data and present it in a user-friendly interface. So this microservice architecture provides several benefits. First one, like it is highly scalable. Each component can scale independently. Then it is resilient. Like if one service fails, another continue to action. So a third one, like it is flexible, like we can replace or update components individually. Now let's discuss the key implementation decisions I made for each component. So first of all, for the data producer, I needed to create realistic sensor data that mimics what we had see from the actual oil pumps. So I implemented algorithms that generates readings within typical range for oil industry equipment with some randomness to simulate natural variation and occasional anomalies. Then I also added configuration options to control the data generation rate. This was important for testing how the system handles different volumes of the data from a few readings per minute to 100 per second. The producer basically connects to the Kafka using a robust connection strategy with automatic reconnection logic. This ensures that even if there is a temporary network issue, our data transmission will resume automatically without manual intervention. Then the next is Kafka implementation. Like for the messaging layer, I choose Apache Kafka because it excels at the handling high throughput data streams in a production environment. This would allows us to process millions of sensor reading per day reliably. One critical pattern I implemented is the dead letter queue, DLQ. If a message cannot be processed correctly, perhaps due to invalid data format or a system error, so it is not lost, but instead it routed to a specific Kafka topic for later inspection or reprocessing. So this is crucial for production system where data lost is unacceptable. Then the next one, I implement the data consumer. So data consumer service has several important responsibilities. Firstly, it consumes message from Kafka using a consumer group. approach, which allows for horizontal scaling by adding more consumer instances if needed. Then for the data storage, I used a transaction-based approach to ensure that a reading is either completely stored in all the relevant tables or not stored at all. So this maintains data consistency even if errors occur during the storage process. Then for the security, I added API key authentication. While simple, it provides a basic level of access control that could be expanded in a production environment. Then talking about database design. So for the database, I carefully design a schema that separate different types of the measurement into the dedicated tables. Like we have the pressure data, we have the material condition, we have the fluid dynamics, we have the viscosity and the flood temperature. So for deployment, I ensure the database schema is automatically created when the application first runs, making setup easy and editable. I also added appropriate indexes to speed up time series queries, which are common in monitoring applications. So the front end is built with Angular and provides an intuitive dashboard for monitoring group performance. And maintenance engineers who need clear visualizations and actionable insights. So I implemented real-time charts using Chart.js that update automatically as the new data arrives. The charts are interactive, allowing users or like uh, to zoom into specific time periods or export data for further analysis. The dashboard also includes summary statics and status indicators that highlight pumps operating outside normal parameters. This helps engineers quickly identify which equipments need attention. Then for the better user experiences, I implemented the responsive design principle so the dashboard works well on the both desktop computers and tablets that engineers might use in the field. So this is all about like my project. Hope you understand it and like enjoy it. Thank you.